Okay, so welcome to section 5 in chapter 24. We have considered R circuits, C circuits, L circuits, and then RC circuits and RL circuits. Now it's time that we consider circuits that has all three elements R, L, and C. So if we have a circuit that has all three elements, something like this figure here, it's called RLC circuit. As you expect, again, we will have the relationship between voltage and I either in their RMS value or in their max or peak values to be V equals to I times Z. But now that we have the three elements in the circuits, what is Z? Now we can define Z by the following equation. Impedance for an RLC circuit equals to square root of R squared plus XL minus XC squared. So it's important to notice that second term under the square root is XL minus XC to the power of 2. Let's just break all the quantities here to their components. So it's going to be square root of R squared plus XL is omega L minus 1 over omega C to the power of 2. Okay, let's see how this is the most general form of the resistance. Imagine that only you have R in the system. So if only R is here, then Z is going to be, because XL and XC will be 0, then Z is going to be R. If I only have R and C, right? Okay, then there is no need to have XL here, so this guy here becomes 0, and negative XC to the power of 2 is XC squared, so Z becomes square root of R squared plus XC squared. Now, if I have R and L components, then there is no need for XC to be here, and then Z becomes square root of R squared plus XL squared. And it is correct for every situation. For example, if I only have inductor, I do not have R here, I do not have XC here, so if I only have L, then Z becomes XL. If I only have C, then Z becomes XC. So it's good to remember the general form of impedance, which works for every combination of the elements. Okay, now that we have three elements in our circuit, it's good to talk about the phasor diagram for an RLC circuit. Okay, for that, I need to draw a big figure for you, and that is figure 24-23 on your book. But because here I do not have the capability of using the colored pen, so I'm going to explain to you one by one what happens to the phasors. Like always, let's start with the phasor for current, the one that has theta equals omega t, the direction with the x-axis, and it's moving with angular frequency omega. Next, we know that voltage across the resistor is in the same direction to the current, so I can write this is I max times R, which is voltage across the resistor. Okay, next go to the capacitor. We know that voltage across the capacitor lags the current, so if I want to draw it, it's going to be 90 degrees behind the current. So this is going to be I max times capacitive reactance, which is lagging the current by 90 degrees. Okay, let's move on to the inductor. Inductor leads the current, so the voltage across the inductor leads the current. Alright, so this is going to be maximum voltage across the inductor. So let's call it I max times X sub L, and this is leading the current by 90 degrees. Next step is to find the difference between the voltage across the capacitor and voltage across the inductor. So if I subtract the two vectors, I'm going to have the difference vector here, right? So this vector is the subtraction of I max XL and I max XC. So let's call this I max XL minus I max XC. And you see that they have 180 degree angle, like they have this like pi angle between them. Alright, now it's time to sum the difference with the voltage across the resistor. So I'm going to do the vector summation now, because they're not along each other. So let me, if I'm very careful. Alright, so this is the vector summation between the voltage across the resistor and the difference of the voltage across capacitor and the inductor. So this is going to be, it's not very straight, but I'm trying my best here. So this is going to be the total of maximum voltage in the circuit that has RLC. So this is going to be V max equals to I max Z, the impedance. Now, the angle between the maximum voltage and the current, maximum current, is something that we called phi. So this is my phi here. Now, if I want to find phi, I can use this equation, that is equation 24.17 on your book. Tangent phi equals to XL minus XC divided by R. And like always, cosine phi is going to be R divided by Z, but here Z is that the general form, the one that has R, XL, and XC in it. Let's try to do example 2415. Draw your phasor. So this is an interesting example. It gives you an AC generator with a frequency of 60 Hertz and an RMS voltage of 120 volts is connected in series with a 175 ohm resistor and a 90 millihenry inductor and a 15 microfarad capacitor. Draw the appropriate phasor diagram for this system and calculate the phase angle phi. So this might be a type of the question that pops up in your final exam. Because this question is all about drawing, so I decided to draw the circuit instead of just writing the known and unknown. So you can see that resistor, the inductor, and the capacitor is shown here, and then the VRMS for the AC generator is 120 volts and its frequency is 60 Hertz. To draw an appropriate phasor diagram, we must first find out the values of XC and XL. Now, these values shows us immediately whether the voltage leads the current or lags behind it. So first, to find XC, I use equation 1 over omega C, and again omega is 2 pi f, and I convert 15 microfarad to farad by multiplying it by 10 to the power of negative 6, and I get 177 ohms for the capacitive reactance. To find XL, I use omega L, which is 2 pi f times inductance, and you convert 90 millihenry to Henry by multiplying it by 10 to the power of negative 3. And then you get 33.9 ohms for the inductive reactance. Okay, now we're talking about drawing the phasor, so we need to know the phase angle, and I'm using equation 2417 to find phi. Alright, so phi is tangent inverse of XL minus XC divided by R, and when you plug in the numbers here, you get the angle to be negative 39.3 degree. Now we can draw the phasor diagram for this circuit. First, the fact that XC is greater than X sub L means that the voltage of the generator lags behind the current and that the phase angle is negative. Next, we need to draw the lengths of the phasors for the voltage across the resistor, across the capacitor, and across the inductor in proportion to the values of R, XC, and XL. Okay, so the fact that we know is that voltage across the resistor is in the direction of the current, so I just plug in these two, I just draw these two, and because I know that phi is negative and XC is bigger than XL, I know that the voltage should lag the current. So I expect, if this is phi here, so I expect my voltage to be along this line. Now let's see how we should draw XC and XL. So I know that the angle between the voltage across the resistor and the voltage across the inductor is 90 degree, and the fact that voltage across the inductor always leads the current. Okay, so but because XL is smaller than XC, I'm going to draw a very small vector here. So this is I max times XL here, but then the I max XC, which is the voltage across the capacitor, and we know that it lags the current, is much bigger here. Okay, let's try to find the difference between the vectors here. And this is going to be I max XC minus I max XL. So I'm just like subtracting the voltage across the capacitor and the voltage across the inductor. Now I'm going to do the vector sum between this difference and then R. So this is going to be my V max, which is equal to I max times Z. And then, as you can see here, the total voltage is lagging the current because phi is negative. There is an example on your book, example 24:16, and I would like you to go ahead and study this yourself. It's a very good example, but let's just put everything that we have learned in section 1, 2, 3, 4, and 5 all together. If you have only resistor, then impedance equals to R. If you have only capacitor, then impedance is equal to XC, which is called capacitive reactance, and equals to 1 over omega C. Now, if you have only if you have only inductor, then impedance equals to X sub L, which is the inductive reactance, equals to omega L. Now, if you have the resistor and the capacitor, then Z equals to square root of R squared plus XC squared. And if you have the resistor and the inductor, then your Z is equal to square root of R squared plus XL squared. If you have all three, then the impedance is equal to square root of R squared plus XL minus XC squared. So the Ohm's law in the most general form is V equals to I Z, and if you have RMS, then both sides should be RMS values, and if you are talking about the peak amount or the maximum amount, then both sides should be maximum amounts. Now, there are equations for the power in each case that you need to study yourself, and for the phase angle that you need to study yourself, and these equations are all on table 24.1 in your book. And this brings us to the end of this section, and shortly we are going to talk about the resonance in electric circuits. Well, stay with me and stay safe and healthy, and like always, please let me know if you have any questions. You can put a comment on the discussion board that we have about this chapter, or you can just leave a comment for me in the YouTube video.